So I thought I would give me a short presentation on myself to start with, because I'm not established researcher with one research field since 15 years back, so I understand that it's a bit confusing what I'm doing, and therefore I thought I would start with just showing that I did my bachelor in Hamburg together with Olaf Pepke, which was a extremely nice time. So I started my research there in environmental chemistry. And I defended my thesis in 2006 at the Department of Environmental Chemistry in Sweden, so I'm Swedish, together with Åke Bergman's group. This is a picture of all of us. And this is me, and this is my best friend, so you see that maybe. And after that I went to Amsterdam, the Netherlands, and worked at the Institute for Environmental Studies for 2.5 years. And that's where I did the work with the Effect Directed Analysis, and what I'm going to present for you. But currently I'm working at the European Commission Center, the Institute for Environment and Sustainability at the Joint Research Center in Italy. This is the outline of the presentation. So I will introduce why we're doing this, a presentation of the EDA project that I was involved in, the MODELKEY, introduce it to the EDA with general aspects about the EDA, and the outcome of the study that I did, where I was focusing on the identification of androgenic compounds in sediment samples. And maybe if I have time, I will add some additional research within MODELKEY and then discuss some difficulties and future needs. And then finally, I will just jump over to the Joint Research Center, the European Commission, and the Lipid project that I do there. And this for two reasons. First, to demonstrate the monitoring studies, general monitoring studies, which the EDA approach is finally aiming to support. And secondly, because this is an ongoing project, but I analyzed some body samples from Brazil, and I thought it could be nice to show it here when I'm here. And also because that's where I work right now, if you want to have an identification of me. So, to start with, the introduction became very simple for me. You just have to remember everything that Wilson Jadim said yesterday. He had a very inspiring talk, so please just remember everything. I don't know if you can do that, but so I want to highlight some of the things that we said. For example, the exposure. He very much talked about why we are looking for these keytoxicants. And we're exposed to germs, genes, and environment, and I added for Roland Weber the unintentional and intentional part of the environmental exposure. And why is that, well, to start with, a large amount of the chemicals produced, there's a large amount of chemicals produced and therefore also available in the environment, and therefore is a highly likely of exposure to occur to us. And these chemicals are not legislated, so there is no control. Wilson used this approach to go for the high production volume chemicals, and this is not what I do, but I think it's very important what he does as well. So the traditional risk assessment approach is based on chemical burden and the resources in good and bad ecological status, whereas this integrated risk assessment approach is evidence-based, using Bioassay directed chemical identification and confirmation. And the resource of this integrated risk assessment was also very nicely stated by Jan. The more we investigate, the more we know we don't know. And I will demonstrate that as well. So I added two studies about chemical analysis versus toxic effect. And one is from Jacobs in 1993. The sediment samples from contaminated sites were analyzed in the US, in the state of Florida. And they used the microtox bioassay. It's a bacterium assay measuring acute toxicity. And simultaneously they analyzed 82 organic priority pollutants. And on an average, and that was they had 105 sediment samples, the toxicity that they observed significantly correlated to the pH and DDE concentration. But this is very many samples, and if you went into an individual sample basis, the conclusion was that there is no correlation, or at least there is a large part where you could not explain the observed high toxicity with the pH and the DE concentration. So the risk is that if you don't analyze any priority pollutants, you deem this area as clean. The second study is performed by Thomas in 2001, and they analyzed water samples from UK rivers after storm, because storm water has been shown to drain out pesticides into the river systems. And they used the Daphnia magma, also a keytoxicity assay, and they did not observe any toxicity in these water samples to begin with. But then they performed a fractionation with the carbon-18 HPLC column, and then they had a toxic effect in the fractions. And they performed the OCP organochlorine pesticide analysis that was expected from the area, and it could explain 11 to 40% of the total observed effect, which I think is a lot. But still, it did not explain the full toxicity, so they did additional chemical analysis, and they did a GCMS screening using MIST libraries to identify the compounds, and they found, for example, nonylphenol and endosulfan sulfate. But what I want to show with this study is that the risk here is that if you don't observe effect, you also deem the area clean, but it might not be true. So there's a need for a combination of chemical analysis and bioassays. So the project MODELKEY that I was involved with is created to support the Water Framework Directive. Just very shortly, the Water Framework Directive is a directive to demands the member states of European countries, the member states of Europe, to take actions to create a good ecological status of all water systems. That includes also up to 1 kilometer from the seashore in oceans. And one of the driving forces, well, that's the demand is that there's a good ecological status before 2015, which is very optimistic, I think. One of the driving forces for an insufficient ecological status is stress factors, and chemical stress is one of the issues. And therefore, my work was to identify the keytoxicants causing this chemical stress. This is the outline of the MODELKEY project. I won't go into it with the different sub-projects, but I want to show you that there is a multidisciplinary approach. And the aim is to develop modeling tools based on effect assessments for the end user to use within the Water Framework Directive. And that's used on 3 case studies. These effect assessments are then effect directed analysis. And it's a combination using bioassays, different fractionation techniques based on physical chemical properties, and chemical analysis techniques. And it starts with, you have a sample extract where the bulk of matrices has been removed. You test it in the bioassays. If the extract is active, it goes into a fractionation. And all these fractions are then again tested, and this is to simplify the matrix. And if they are not active, they are discarded, and if they are active, they go to chemical analysis. And with traditional chemical analysis methods, you can often detect the most common compounds like GCMS or LCMS techniques. But often it's too complex matrix, and you need either further fractionation steps and also in combination with identification strategies. And that's where I work. I will present for you now. So you use different identification strategies. You get a list of possible compounds, and these have to be confirmed both with the effect in the bioassay and analytically in the chemical analytical instrument before they can be put on the list of toxicants. So the analytical confirmation, evidence on chemical structures, and the effect confirmation, evidence of cause-effect relationships, are only two of the confirmation steps. This has been published by Jana Weiss in 2008. What you also need to do is the quantification of the individual toxicants and calculate the contribution to the observed toxicity. And there you can estimate how much is unexplained. And hopefully it's a very low number that's unexplained. But you also have this last hazard confirmation, which is evidence of cause-effect relationships at realistic exposure conditions on populations and communities. That is this keytoxicant actually pose a risk in the ecosystem? This step takes into account also field conditions such as bioavailability, mixture toxicity, individual differences, and very rarely the EDA studies comes to the hazard confirmation. So to kind of sum up, there's a toxicity profiling of the sample first performed in vivo and in vitro with the screening. And here we need those sensitive bioassays. The active sample extract goes further to Effect Directed Analysis approach, and then you get the list of identified keytoxicants, and the ultimate goal is to supply these keytoxicants to national and international monitoring programs, such as the Stockholm Convention's priority list and the Water Framework Directive's priority chemicals. And often you also need to do some target analysis development for these compounds. I just added this to show you the development of this kind of approach. I searched effect-directed analysis in brackets in PubMed, and you see an increase from 2000 and going upwards, and there's still not many publications. There's 12 publications with this exact formulation of word. Of course, there are more studies that supports the effect-directed analysis, and 2010 is not over yet, so I hope more comes here. I also a similar approach is, of course, the toxicity identification evaluation stated by the US EPA. So I also did that search, and there's also an increasing trend, but it's been a little bit stayed on the same level the last year. And for fun, Jana Weiss is working in Leipzig University at the Department for Effect-Directed Analysis, and he's like the EDA guy, and he's also the chairman of the MODELKEY project. This is how much he's involved in these publications. I got the question, who is the EDA guy, right? So the case studies were performed in 3 river systems in Europe, and that is the river Elbe, flowing through the Czech Republic and Germany, and it's surrounded by some 25 million people, and it's considered a very heavily industrialized. The status of Elbe has improved the last years, but it's still a polluted river. The second is the river Scheldt, and runs from France through Belgium and the Netherlands and out in the North Sea. It's considered the most polluted water system in West Europe, but also improving. The river Lipid in Spain is surrounded by 3 million people, but flows through highly polluted areas. It's a very agricultural area, and you have a lot of runoff from that. So first, toxicity profiling on these samples were performed, and this is the battery of bioassays that is used to measure the genotoxicity and the endocrine disruption. And also there's an antibiotic assay in here. And here you have the 3 samples from Elbe, 3 from Llobregat, and 4 from the river Scheldt. I work with androgenicity, and there are 2 different assays. There's the yeast assay and the AR calyx based on a human cell, measuring both the agonistic and the antagonistic androgenicity. So these are the fractions of interest, and you can see here that the Scheldt sample here, this is from a tributary called the Schijn, and it's in Dutch, you have to say Schijn. is an industry area in Eenhoorn, close to Antwerp. So this sediment sample, one sediment sample, I will give you the results for androgenicity. And as you see here, it's antagonistic, but no agonism is measured in this fraction, in this extract. But I want to stress here also, it's very difficult to find a true reference sample. The Lipid A1 was, for example, selected because they thought this was going to be a clean area. You still observed effects. It's the same as this one, I think, Terneuzen was also thought to be clean. So I will show you later why we need reference samples to compare to. So what I did, I used photograms of sediment, I sieved it and freeze-dried, and it's accelerated solvent extracted. Accrued fractionation with the GPC, where you have the matrix effect diluting in the beginning, and this is the compounds of interest diluting. Here you have sulfur, which you have to cut out because it disturbs the bioassay. And we took a late fraction as well to see if there were any late diluting compounds. And the bioassay is the K-lux, measuring both the agonistic and antagonistic androgenicity. And it was only this fraction that was active. We didn't test this one, of course. And it was further fractionated on the reversed phase LC into 5 fractions with distinct octanol water coefficient spans. So we know exactly it's increasing octanol water coefficient here. We also had one non-polar fraction when there were some compounds that were not possible to dissolve in the methanol, which was the running solvent in the LC. These 3 fractions, the reverse phase fraction 2, 3, and 4, were active, and they were further fractionated on the normal phase fraction with the increasing polarity. And we did, again, all the bioassays on this fraction, and we could identify some active fractions. It's also on the normal phase fractions that the chemical analysis are performed on, because they are the least complex fractions. So the bioassays result, we could clearly get 3 distinct groups of compounds with increasing polarity. These are the reverse phase fraction 1, 2, 3, 4, 5, and the normal phase fraction. And we have in the rather non-polar fraction, normal phase fraction 2 here, we have anti-androgenic activity, as well as the slightly more polar fraction, and we could measure the androgenic activity in the polar fraction, normal phase fraction 7. But as I want to show you here, this is the GPC extract. The potency is decreasing after each fractionation step. But this, we believe, is not due to low recovery, because what we did is we took all the normal phase fraction, we pulled them again, and we could gain the reverse phase fraction potency back again. So we haven't lost any compounds. So it's more due to probably presence of partial agonists, or also the low sensitivity in the bioassay. So if you spread out all the different compounds, you cannot measure it anymore in the bioassay. I could not pull the reverse phase fractions together, unfortunately, to prove we could get this back as well. With androgenicity, we can see that there is no potency found in the extract, but after reverse phase fractionation was a high increase, and even more after normal phase fractionation, which shows, of course, that this is a separation of disrupting antagonistic compounds here. And also here, when we pulled the normal phase fraction, we gained again the lower potency. And this shows that screening of extract did not reveal the full androgenic potency, just like the study with Thomas earlier also. So we performed chemical analysis on GCMS screening. We did the 5-column ionization, mass spectra deconvoluted using AMDIS, and NIST search with a match factor above 80%. And within the MODELKEY project, there was a database developed called the Quality Peak Identification Database, where you use the COVAX retention index to identify the compounds and also to be able to compare the spectra between labs. And this database was also used so you could do background subtraction. So you consider the adjacent non-active fraction as a control sample, kind of, and you could take away many of the compounds present in the background that's not of interest. And the results, this is the non-polar fraction, normal phase fraction 2 with anti-androgenicity. We had a whole cluster with PAHs, but also terphenyl and other aromatic systems. With the more polar fraction, the normal phase fraction 5, we have a very clear here distinct cluster of technical non-nil phenol. So many of the peaks were identified there. And we have phthalates, benzamide, some other compounds. There were 17 compounds in total identified with this approach with Andy's NIST search. And in the androgenic fraction, we only found a cluster of organophosphoric acids. No other compounds. We'll come back to that. But we did not perform any target analysis of any of the priority compounds either by the Water Framework Directive or the Stockholm Convention. According to literature, these compounds are anti-androgenic, confirming our finding. We also performed a complementary LCMS technique with the LTQ-Orbitrap, and we used this instrument because it had accurate mass capabilities, and that's what we based the identification strategy on. And we used software seed from Thermo Fisher, which is a software developed for peptide analysis in a two-group control study. So you have a control and you have a active sample, and then it performs chromatogram alignment of these two and a base framing of the accurate masses that's found. Then it gives you the statistical change between the control and the active fraction or sample. But this software was not really finished developed, so it had some problems with the quality of the peaks that it selected and presented to me in an Excel sheet. So I had to manually check all the peaks, because sometimes it could select a baseline elevation as a peak, or even the isotope. The compound was present at very high concentration. The M+1 or M+2 was selected as a peak as well, so I had to compare that manually. So I get a whole list with the accurate masses, the retention time, and the ratio between the active and non-active fraction. And from here I used the adjacent non-active fraction as the control. And also I had a laboratory blank that I used as control. So these accurate masses are then put in the elemental composition tool in Excalibur. We get a chemical formula suggestion. I tested it in NIST. And if there was a chemical formula that corresponded to compound in NIST, I calculated the octanol water coefficient for this compound and confirmed if it's possible to be in this fraction. So finally we have a list of tentatively identified compounds. We have to purchase them, analyze them to confirm their presence, and perform a bioassay confirmation. So finally we have a list of confirmed compounds. This is published now, this is submitted but not yet accepted to Environmental Science and Technology. So there are some limitations with this approach, and we also had to do some selections. For example, I show you that seed presented to me in these active fractions, almost 15,000 possible accurate masses, peaks. If I look at the ratio between control and active fraction, we decided to go for a ratio above 100, so the increase has to be 100 more in the active fraction than in the control. And this is we could not work with 3,000 suggestions right now. I mean, we hope to automatize it, and of course an increase with 2 could be interesting as well, but so this is one of the limitations. So we worked with 259 masses, accurate masses. And then one of the limitations is, of course, it has to exist in NIST. That's the library we use now. There is some small LCMS library in NIST as well that was used, but it's a very GCMS-directed library, and we will lose a lot of possible polar compounds in this library. It's not in there. Another problem was the possibility to purchase these compounds. So we had 95 tentatively identified compounds of the 259. Optimal, we would buy 95 compounds, but many of them didn't have cost numbers. You cannot get them in high purity. What we did was only a fast screening of the major suppliers, and we were able to purchase 22 of these, which is not so good, but anyway, we go on. Of these 22, we can confirm analytically 10, and on the Bioassay 8. So finally we have 8 confirmed keytoxicants. It's not so optimistic, but anyway. So we decided to work with 2% of the forest of peaks, which is a good limitation. And of the one that we purchased, 36% could be confirmed. And of course, if we were able to purchase all these 95, maybe we could have confirmed some 30-40 compounds. On these 8 compounds, there are 3 MOS compounds, 2 organophosphates, and 1 oxygenated pH, 2 steroids. This one is the only one that was androgenic. This one is strong anti-androgenic, of course it's androgen, and also poses some androgenicity, very weak. So this is an example of a partial agonist. Androstenone is used in pig farming, and not especially, but also in Belgium to a high quantity. So it's a legal drug. It's a pheromone that we use in the pig farming. Nandrolone is an illegal drug used for tissue enlargement, both for humans, of course, it's an anabolic steroid, but also in cattle industry could be used. Benzantron is a dye intermediate, but also coming from combustion sources. I don't have to explain what musks are, and organophosphates are used both as pesticides and flame retardants. But what I want to show you with this chromatogram is that these 2 both steroids, it was very likely that they are a whole isomer cluster. So this is the nandrolone peak, it's just one small peak, it's not the major peak of the nandrolone. Come back to that. So we did an effect confirmation. We tested all these compounds in the bioassay and expressed on the flutamide relative potency. We see here that the most potent was androstenone, followed by the pH, fluorantine, and the MOS compounds. And we performed target analysis of these compounds. Highest concentration is the organophosphate. Together, the pH is together, I would say. And we also had some indication triclosan was present in the GCMS group. So we did target analysis on the triclosan, and it was present. Has not yet been determined on the bioassay, but according to literature, it's anti-androgenic. But that was an in vivo study. So we don't know if that's based on, as the AR calyx is based on the androgen receptor, we don't know the mechanism of triclosan. Skip this one, but look at the flutamide equivalence on picomole per gram dry weight of sediment. We sum up, it's 1,862, but this is just a small fraction of the total potency of the normal phase fractions. It was 59,000 picomole per gram dry weight, or 59 nanomole, and this is only 2 nanomole that we could explain with this approach. But I also want you to this is unpublished data. I want you to notice that it's rather high concentrations that we find with this approach. It's all about 1 nanogram per gram dry weight of sediments, and I compare this with another study we do right now. We analyze Danube sediment from the river Danube. And if you look at the organic chlorine pesticide, for example, the average levels are below 1 nanogram. Maximum level in one sample was 21 for DDE. I added endosulfan, and it's also the maximum level is below 1. So we cannot detect these compounds with this method. We had the possibility to do also a hazard confirmation step, which was very, very nice. In Belgium, they are doing an in vivo sediment contact test with a mud snail, the Pollutants antipodarum. And this is an invasive species, originally from New Zealand, but is established in all Europe. And is known to be very tolerant to natural stressors, but sensitive to endocrine disruption. So it should be a very nice, it is a very nice species to work with. What they did was they got the field sediments from the MODELKEY project. They exposed the snails with the field sediments, and the endpoint they measured with growth and reproduction. And since we're interested in androgenicity, I will only talk about reproduction now. So this is published by Claudia Schmidt in 2010. These are the different samples from Elberskelett and Llobregat. And this is the sample that I present to you here from Enholm. And it shows increased production due to influence of present estrogenic or anti-androgenic compounds. So this confirms that this fraction is anti-androgenic, among others. So what we did is that we sent 2 of the compounds, the androstenone because it was most potent, and the benzantron because its increasing interest for this compound is identified in sediment in several places. And we spiked artificial sediment and made a contact test with the snail. And the androstenone did not show any increasing reproduction at all. But the benzantron had very nice effect dose relationship. And the EC50 here is 6.6 microgram per kilo, or nanogram per gram. And the benzantron concentration that was target analyzed in all the sediment samples were found between 17 and 1460 nanogram per gram dry weight. So this EC50 is at an environmentally relevant concentration, did all this. And I think in Enholm it was 31 nanogram per gram dry weight. But you can discuss now that you remember the relative potency was not very high for benzantron. But this is also measuring the androgen receptor mechanism. And maybe in the reproduction we have other mechanisms as well, so maybe the benzantron is more potent anti-androgenic compound on other levels in the androgenic system. It's also not published. But still, we cannot explain much of all this observed effect here, and that's due to 2 aspects, of course, the limitation of the bioassay. We have synergism between compounds that I showed that can complicate the picture. Detection limits, very nice to see that someone's working on increasing detection limits, really like that. And also that was mentioned very shortly by you was that you have possible matrix effects in the bioassays. On the chemical side, is of course that very potent toxicant can have low concentration and we won't detect them in this way, so we have to improve that. And there is also high detection limit for many of the compounds and with the LC techniques where you can get accurate masses, but they are not possible to ionize with the soft ionization technique. We need a bigger spectral database to search for the compounds. And so the research needs bioassay screens development for high throughput. They have to be cheaper. The AR calyx is very expensive, but it's also very sensitive, so it's a good assay because of that. Evaluation evaluation of alternative chemical analysis techniques to improve the detection limit, and sharing the information. And the Norman network just started a EDA work group, and they are discussing this, how to share the spectral libraries between labs. Also within the field of omics, genomics, metabolomics, they have the same problems, and we should merge the efforts to solve this, because they also need to identify key compounds in a huge amount of, whatever they measure. We need to evaluate software, how we can handle these immense data sets, done together with the field of omics. And finally, optimize this, because we have, it's too laborious, and working on one sample takes a year at least. To sum up, I want to show you that the samples we identified as keytoxicants are the PAHs. They are on the Water Framework Directive priority list, but not the oxy-PAH. There is no regulation on it. Non-phenol is also on the list. There is one candidate substance to the priority list. Organophosphates, I could not find any regulation except for food safety in US EPA. I don't know if I just missed it, if someone knows more about regulation for them. The steroids are under pharmaceutical regulation. I assume they are, I don't know with these compounds, but since they are isomer clusters, maybe not all of them are detected. The musk, you have a xylene musk that is a candidate substance, but not the polycyclic musk that I identified here. But none of these were then the Stockholm Convention priority compounds, and that is of course due to that these compounds have very, very low concentrations that I cannot detect. And I would like to acknowledge then all the co-workers here. I worked mainly with Maria and Pim and Tina, and also with Esther. The bioassays were performed at BDS in Amsterdam, and the LTQ-Orbitrap was at the Waterdienst in Lillestedt. And these are references. This is where I work right now. I live here. This is the Rocca, the castle bottomy, and you have Lago Maggiore behind here, and this is Monte Rosa. That's Switzerland's highest mountain, 4,600 something. It's a very beautiful area. So I don't know how familiar you are, but the European Commission have 7 research centers in Europe, and where I work in Espoo, Italy, is the largest one. It has 3 institutes. It's the Institute for Protection and the Security of the Citizen, Health and Consumer Protection, and Environment and Sustainability, where I work. And this is permanent staff, around 900, but we have also the administration, we have guest researchers, we have grant holders like me, and we have daily visitors due to conferences, courses, etc. So there is around almost 2,000 people at the center every day. But the total permanent position for all the 7 joint research centers is 2,200. And the mission of the center is to provide customer-driven scientific and technical support for the conception, development, implementation, and monitoring of EU policies. And that is, for example, the Water Framework Directive, Stockholm Convention, etc. So we are supporting. So going to the project that I'm doing now, I want to show you some background. Many people know about this paper performed by Kalansi and Kevin Jones is in here also, where they did a global butter analysis to see the distribution of dioxin, PCBs, and some selected pesticides. And they have butter from 22 countries, sample 99-98. And similar, at the same time, we analyzed butter from 37 countries for PCBs, dioxin, PCB, and some pesticides. And together these 2 studies covered 44 countries. And the funny part, this is published in 2001 and this 2005. But we presented at the same time at the Dioxin conference in Korea in 2001, and they actually put us after each other. I think I was first, right? And then Kalansi came up for the presentation. And it was funny because the studies have been done independent of each other, but they were identical. And we also had comparable levels, which was really nice, and we were confirming each other. And this was done together with Olaf Peckel and in Hamburg. Now I have a similar project, so I've gone from EDAs back to body samples again. In the Lipid project at the center, and the long title is EU-wide Lipid Monitoring of Dioxin POPs and Emerging Pollutants, Calibration of a Monitoring System for Regional Multimedia Environmental Concentration. But we call it Lipid Project, you see. The thing is, we want to show, this is not a human exposure study, but we want to show that animal lipids can be used as biomonitors to get an indication of the air concentration of POPs in a region. And we analyzed for all the Stockholm Convention's POPs, the dioxin PCBs, PVDs, and 29 OTPs. And why lipids? We heard yesterday about passive samplers, and of course they're good. But lipids also reflects the, they are very good matrix for being a passive sampler due to well-known transfer factors. And here are two examples that McLachlan in 1997 calculated that the daily intake of a lactating cow by grazing is equivalent to an intake from breeding approximately 100,000 cubic meter of air. Another study showed that more than half a kilo of dioxins are estimated to be transferred annually from the atmosphere to the UK pastures. The advantage is that they are available in all geographic regions. They are cheap, commercially available. They are buffered against temporal variations. And there's a high bioaccumulation due to the POP's properties, with the lipophilic properties. And the most important advantage compared to all the passive active samplers is that no advanced equipment or trained personnel even is needed. You only have to go to the farmer and get some butter, and everyone can do that. The disadvantage is, of course, that there's not a controlled exposure. We don't know what's fed by, what they get in by feed, or if they chew on the barn or something, I don't know. But if they're commercial samples, they can be pooled samples from a very large area. And of course, we can only measure the lipophilic compounds. But they are not controlled exposure. This can be taken care of, and also from large areas, this can be controlled. But the message is that we want to use the lipid monitoring for first screening, and of course, then afterwards, if you there's an area with a problem, you can go in detail and set up all the stations and everything, but this is the cheapest way to get an idea to start with. So we have 3 batches. One is 88 milk samples directly taken from farmers in 2001, and 2007 they went out and collected bio-certified produced butter. They are commercial, but they are not supposed to be exposed to pesticides. So it should be the air levels. In 2009, now I have been sent by the Global Monitoring Network and other people also some body samples and milk samples from other continents. And we want to compare that to available air data, and especially based on EMAP, which has 28 stations in 15 countries. And we hope to get something like this. I mean, this is an ongoing project. This is just an example how it could look like. Well, actually, these are analyzed samples from 2001 on IHH. And here you have Belgium and the Netherlands, and you see that we have a hotspot area here. And we compared at the 2006 EMAP air data, and we also identified a hotspot area at the same place. And this is what we hope to find when we go on the EU level. So we're going to confirm this model on EU level, and then hope to go further to confirm it in other countries. As you've heard already, endosulfan has been suggested to be on the NXA list, and it's banned in more than 60 countries, but still in use in Brazil. And endosulfan sulfate is the transformation product that we can analyze for in butter. This is the European results. I lack some samples from here and here. They are still analyzed. You can see that an average is 1.3 nanogram per gram lipid weight, with a maximum in Germany here with 6 nanogram. This is well below the maximum residue level set by EU of 50 nanogram per gram lipid weight. And here I added also the HH, the dealdrin, the heptachlor epoxide, that's also the transformation product of the heptachlor that we identify in butter, the DDT, and then the sulfane sulfate. And this is European butter from 2007 and 67 samples. And this is the normal pattern. I added Italy because I live there, and you can see that it's a very similar range there. And this is the Brazil butter, 3 samples. They're very low in the pesticide except for the endosulfane sulfate, really showing that the ongoing use there. And this is exactly what we want to use the data for, kind of. So, unpublished data. I just want to mention, in the 2000 sample that we analyzed, there was a Brazilian, we only had one Brazilian sample at the time, from São Paulo, I think. And there the DDE level was 25 nanogram per gram, which is similar as the maximum here in East Europe. This is DDE-DDT levels in butter in 2007. I can't remember. I need data from Spain. That's why I want to show this. I kind of used this opportunity for you to kind of contact me interested to start a sampling campaign with butter. It's easy. Analyze them for the OGPs. I also want to show that I compared 1998 with 2000 sample and 2007 samples in European countries, and I think it's very nice to see how well the 3 studies, although they are different over a span of almost 10 years, we see the same profile of the DDT levels. I'm specifically asked for Ukrainian butter. I have it in the fridge now. I have to confirm this one. It's 171,000. This is 100,000. It's twice as much. Yeah. So, yeah, this is the request. And I want to thank you again for presentation.
Thank you very much. The topic is very interesting, both parts of it. In fact, we are going to see in the afternoon session some indications that endosulfan in air also. But my comment and question is related to pyretroids. Because one student of Professor Olaf did her PhD with us in cooperation with other colleagues from the Mato Grosso University, and she collected butter and found pyretroids. Have you ever measured it?
No. You don't either right now. No, but if that's an indication they exist, I will take it home.
One question. When you mean extract, for the first part of your lecture, you mean organic extract or water extract?
We use, that's an accelerated solvent extraction. And we use a combination of the chloromethane and acetone, and we hope to include the polar compounds with that extraction.
Okay, but how can you distinguish the effect from the organic solvent from the exactly in bioassay? You can diminish the effect of the solvent?
Yes, it's dissolved in DMSO for the bioassays. So why I start with 40 grams of sediment sample is a lot. Is to be able to always take a fraction for the bioassays. So I evaporate the solvent, I dissolve it in DMSO for the bioassay, and we have DMSO blank also, so it should not affect the bioassay.
So you evaporate all the solvent. So you can also lose some volatile compounds.
That's a big problem, the volatile compounds, yes. We try to be as careful as possible, but of course that's one of the compounds that probably will be lost. Because there's also many steps, and if you do the reverse phase fractionation, for example, you have a higher volume afterwards. After the fractionation, you have a liter. So you have to roll to evaporate. And we keep down the temperature still, yes, that's a problem.
And another question is about considering integrate anthropogenic sources, considering all the factor or the hormone or the agriculture, whatever. How is our the main attention in Europe, for example? Consider all the sources.
You mean the natural sources?
No. The anthropogenic. Which is the main concern nowadays? It's always pesticides, oil industry, pharmaceuticals.
Well, in the world of EDA, I would say, we're going way far away from the Stockholm Convention's priority compounds, at least. That's not the main concern. The main concern is probably high production volume compounds, having a low toxicity but extremely high concentration. And there is, pesticides is always a problem. They're always there also as a problem. But if you look at what I analyzed, for example, is phthalates, they're not very potent, but there are immense amounts of them out there. And also the musks come from industry, our usage, of course, and that the sewage treatment plants cannot eliminate them totally. But it's a combination, I think, of all of it. I don't know how the community is looking at the major problems, but EDA shows that there's a combination of problems from different sources. Also oil, of course, the pHs and everything.
I think you understand well. You got the butter, commercial butter, you don't go direct to the producer.
The 2001 is directly from the farmer, so we have good coordinates. And the 2007 is commercial butter.
Yeah, this was very interesting kind of monitoring using. But how exactly was calculated how much butter represents of the air? How secure is this dimension?
Probably not very, because as I said, we don't have a controlled exposure. We have models performed on one cow and see how it's transferred. And we have very nice correlations between air glass cow milk, and so on. But I would say it's a really high uncertainty factor. You cannot look at the numbers, but you can look at the indications, so you can compare areas, I would say. So to calculate exact concentration in air, I would be a bit careful.
More rain, no?
Yeah. So,
yeah.